Welcome to the third video in our series on the reactor design case study in Module 11. Believe it or not, you've already done all of the math that you need to do in order to solve this problem. You'll see in each slide of this video that we refer to questions. These questions are the questions in which we did a calculation variant on the information that's presented in the slide. If you're having any difficulty understanding the video, you can refer back to this question to get a better sense of the underlying mathematics. I encourage you to pause the video along the way and try to complete each step of the analysis yourself. This will help to strengthen your core skills while you look at how to put together a complex problem. With this in mind, let's review. We recall that we split our problem into two tasks. The first we completed in the last video. That was determining the optimal reactor shape and size to maximize production. And now we'll tackle the second task of selecting the appropriate material to maximize return on capital, which is defined as dollars earned per dollar invested in order to build the reactor. We broke down the information that was given to us in the problem statement into three categories based on information that we can deduce from it. First, we're able to calculate the number of liters of material produced per hour because we have the surface area of the reactor, which is used to transmit heat that drives the reaction, with 10 units of heat being needed per liter of reactant. And we also have the heat transfer coefficient, C, for each possible material. This gives the amount of heat that's transmitted per meter square of surface area. With this information, we can calculate profit, which is equal to revenue minus expense. We know that each liter of product brings in 10 cents of revenue, so with the number of liters per hour, we can calculate the revenue per hour and subtract from this the expense of the cost of utilities to get profit. And finally, we can calculate the cost to build the reactor because we know the size of our reactor from our previous step, and we can calculate the cost of material based on the function plot that was provided to us in the problem statement. So, our strategy to attack the issue of maximizing return on capital is to write an equation for liters per hour produced, and from that, calculate profit per hour. Then we'll calculate the payback time for each material. The shortest payback time is that which earns the most money per dollar invested, or the greatest return on capital. So we'll select our material based on this. From the previous module, we have the geometry of the reactor with a 4 by 4 meter square base and a 25 meter height. Its actual surface area would thus be 432 square meters, and its effective surface area, that is, the surface area discounted for the failure rate, is 397 square meters. So let's systematically attack each step in our strategy with this information in mind. First, we write an equation for the number of liters per hour produced. Recall that we have the surface area A, as well as C, the number of units of heat per meter squared surface area per hour for each material. So C times A will give us the units of heat per hour transmitted for a given material. We can then convert this into liters reacted because we know that 10 units per liter of heat are needed to react. So 0.1 Ca gives us the number of liters produced per hour. Plugging in our effective surface area of 39.7 square meters gives us a liter per hour production of 39.7 C. From liters per hour, we can calculate profit per hour. The profit is equal to the revenue minus the expense. We have liters per hour from the previous module, and we know that how much revenue is brought in per liter. So we can multiply revenue by the number of liters per hour produced to obtain a revenue of $3.97 times C per hour. And we know that our expense is fixed at $675 per hour. So our profit is $3.97 times C minus $675. Now that we know our profit per hour, we can calculate the payback time for the material. We were given this chart with the problem statement. This gives us the number of square meters, the cost per square meter of material as a function of the number of square meters of material ordered. In this case, our surface area was 432 square meters. So in order to get the cost for this material per square meter, we draw a vertical line at 432 square meters ordered, and then walk over to the y-axis for each function value in order to get the corresponding price. Doing so gives us a price for P equal to $240,000 per square meter, Q $275,000, R $325,000, and S $675,000. A pretty expensive reactor indeed. We then calculate the cost to build the reactor for each material. We plug in the price per meter squared and multiply this by the area, so we can calculate the cost to build the reactor in millions of dollars. It's best to use Excel for information like this so that we can store the information and keep it organized. Once we have the cost to build, we can calculate the payback time. The payback time is the number of hours for which the revenue minus the expense or the profit times the hours is equal to the cost of building the reactor. So we calculate each metric for each reactor. We create a row for our price as well as our heat transfer coefficient. Our revenue is equal to our area times our heat transfer coefficient times our heat requirement, times revenue divided by the heat requirement multiplied by the success rate. And from this we can calculate the revenue per hour. Utilities are fixed at $675 for each reactor, and the cost to build we calculated in the previous step. The payback time is the number of hours, so we solve the equation that we wrote for the payback time for the number of hours. In order to do so, we divide each side of the equation by the difference between the revenue per hour and the cost of utilities per hour, or the profit. So the payback time in hours is equal to the cost of the reactor divided by the profit per hour. We can execute this in Excel very simply. We simply take the cost to build and divide it by the difference between revenue and utilities. This gives us the number of payback hours for each reactor. It makes sense to convert into a more reasonable metric, since the payback hour value of 30,000 doesn't necessarily give us a good sense of exactly how long our payback time is. In order to do so, we can divide by 365 times 24, the number of hours in a year, to calculate payback years. And we can see that the reactor material with the shortest payback time is R, with a payback time of 2.3 years. Recall that low payback means that there's a high ratio of the number of dollars earned compared to the number of dollars invested. Our return on capital is equivalent to dollars earned compared to dollars investment. So, low payback means that there's a high return on capital. Since we want to select material with the highest return on capital, we want to select the material with the lowest payback for the reactor, which is a reactor made of material R. Now that we've solved our problem, we take some time to look back. We went through a lot of steps here, and it's worthwhile to think about how we would communicate this result. What information would we include? We could also think about other approaches to our solution. We did a lot of work out in Scratch and in Excel. Were there alternative ways to solve this? Are there better ways to organize the information? And finally, we asked the question of how results compared to our expectations. Certainly it was unexpected that a more expensive material would actually be the best investment. And this shows the importance of the relationship between cost and performance in determining which material was most advantageous. Now that you've had a chance to walk through this problem, it would be very helpful to go and try to solve it again yourself. Once you solve the problem, watch the videos again and compare what you did to the systematic problem-solving method that we employed here. And finally, communication is important in every problem-solving process. You need to learn to communicate your thought process effectively and in a clear manner. As an exercise, it would be worthwhile to take this case study and attempt to write a small report or a short solution memo that would communicate the information that's most necessary for a pre-specified audience. You could think of writing this for your boss at work, or even to explain to a friend the work that you did. You might also consider trying to generate a PowerPoint presentation to explain what was done.